What is the shape of the universe? It sounds like a simple question, but it's one of the biggest questions you can ask. The answer is not simple. It's not a shape like a ball or a box. When scientists talk about the shape of the universe, they mean something different. They are talking about its geometry. They are asking if space is flat or if it's curved. And if it's curved, how is it curved? To get a handle on this, let's forget about the whole three-dimensional universe for a second. Let's imagine a two-dimensional universe. Imagine you are a perfectly flat ant living on a giant, infinite sheet of paper. Your whole world is this flat surface. You can move forward and backward, left and right. But there is no up or down. On this flat sheet of paper, the rules of geometry you learned in school work perfectly. If you draw a triangle, its three angles will always add up to 180 degrees. If you and a friend start walking in parallel lines, you will stay parallel forever. You will never meet, and you will never get farther apart. This is what cosmologists call a flat universe. It's Euclidean. It's what we experience in our everyday lives. But what if your 2D universe wasn't a flat sheet of paper? What if you lived on the surface of a giant sphere? You are still a flat ant. You can't perceive the third dimension. You don't know you are on a ball, you just know the rules of your world. On this sphere, geometry is different. If you and your friends start walking in parallel lines from the equator heading north, you will slowly get closer and closer. Eventually, you will bump into each other at the North Pole. Parallel lines meet. That's weird. If you draw a big enough triangle on the sphere, its angles will add up to more than 180 degrees. This is a universe with positive curvature. It's also called a closed universe. A key thing about this universe is that it's finite. You can walk in one direction long enough and end up right back where you started. But it has no edge. You'll never fall off, you just keep walking on the surface. Now imagine a third option. What if your 2D universe was shaped like a saddle, or a Pringles chip? A surface that curves in two different directions. This shape is called a hyperboloid. If you and your friends start walking on parallel lines on this saddle-shaped world, you will get farther and farther apart. Your parallel lines will diverge, and if you draw a triangle, its angles will add up to less than 180 degrees. This is a universe with negative curvature. It's also called an open universe. This kind of universe is infinite. It goes on forever in every direction. So, we have three basic possibilities for the geometry of the universe. It can be flat, like a sheet of paper. It can be positively curved, like a sphere. Or it can be negatively curved, like a saddle. Our three-dimensional universe would be curving in a fourth spatial dimension we can't perceive, just like the 2D ant couldn't perceive the third dimension his paper was curving in. The big question is, which one is ours? Is our universe flat, closed, or open? How do we figure this out? We can't go outside the universe and look at its shape, we have to measure it from the inside. And it turns out the geometry of the universe is directly connected to how much stuff is in it. The stuff is matter and energy. Einstein's theory of general relativity tells us that matter and energy warp spacetime. The more stuff, the more warp. So the question, what is the shape of the universe, becomes how much stuff is in the universe. There is a magic number called the critical density. This is the exact amount of stuff per cubic meter the universe would need to be perfectly flat. It's a very small number, about 5 hydrogen atoms per cubic meter, but it's the balancing point. If the actual density of the universe is equal to the critical density, the universe is flat. Its geometry is Euclidean. It will expand forever, but the rate of expansion will get slower and slower, approaching zero. If the actual density of the universe is greater than the critical density, there's a lot of stuff. The gravity from all the stuff is strong. It will curve space back on itself, like a sphere. This would be a closed universe. In this scenario, the universe's expansion would eventually stop, reverse, and collapse in on itself in a big crunch. Well, if the actual density of the universe is less than the critical density, there isn't enough stuff. Gravity isn't strong enough to stop the expansion. The universe would be negatively curved, like a saddle. It would be an open universe that expands forever, and the expansion would never really slow down much. So, all we have to do is count up all the stuff in the universe and compare it to the critical density. Simple, right? Not really. This turned out to be one of the hardest jobs in science. For decades, astronomers tried to do this. They counted up all the stars, galaxies, and gas clouds they could see. If they measured all the visible matter. When they added it all up, they got a number that was way too small. It was only about 5% of the critical density. This suggested we lived in an open, negatively curved universe that would expand forever. The case seemed closed, but then things got weird. Astronomers noticed that galaxies were spinning too fast. The stars on the outer edges were moving so quickly they should have been flung off into space. The gravity from the visible stars and gas wasn't nearly enough to hold the galaxy together. It was as if there was some invisible mass, a halo of stuff around the galaxy, providing the extra gravity needed. They called this stuff dark matter. They found more evidence for it. They saw how light from distant galaxies was being bent by the gravity of galaxy clusters in front of them. The amount of bending suggested there was way more mass in the clusters than we could see. Dark matter wasn't just a weird theory, its gravitational effects were visible everywhere. So scientists added dark matter to the cosmic inventory. It turned out there was a lot of it. About 5 times more dark matter than regular matter. So now, our total density was about 30% of the critical density. Still not enough to make the universe flat. It was still less than 1. The evidence still pointed to an open saddle-shaped universe. And that's how things stood for a while. The best guess was an open universe. Then came the second, even bigger shock. In the late 1990s, 2 teams of astronomers were trying to measure how much the expansion of the universe was slowing down. They were using a specific kind of exploding star, a type Ia supernova, as a standard candle. These supernovas always explode with roughly the same brightness, so by measuring how faint they appear, we can tell how far away they are. And by measuring their redshift, we can tell how fast they are moving away from us. They expected to find that the expansion was slowing down due to gravity, but they found the exact opposite. The very distant supernovas were fainter than they should have been. This meant they were farther away than expected. The only way for that to be true was if the expansion of the universe was not slowing down, but speeding up. It was accelerating. This was a bombshell. Something was pushing the universe apart. A kind of anti-gravity force that acts over vast distances. No one knew what it was. They gave it a name, dark energy. This dark energy had to be included in the cosmic inventory. And it turns out it's the biggest player in the game. When you calculate how much dark energy there must be to cause the acceleration we see, it accounts for about 70% of everything in the universe. So now let's add it all up again. We have about 5% normal matter, about 25% dark matter, and about 70% dark energy. What does that equal? It equals 100%. The total density of stuff in our universe, once you include dark matter and dark energy, is almost exactly equal to the critical density. This was a stunning result. It meant the universe is not open, it's not closed, the universe is flat. Its geometry on the largest scales is the simple Euclidean geometry we learn in school. The parallel lines stay parallel. The angles of a giant cosmic triangle would add up to 180 degrees. This was a huge discovery, but scientists needed more proof. An answer this important can't rely on just one type of evidence. The confirmation came from the most ancient light in the universe. It's called the Cosmic Microwave Background, or CMB. This is the afterglow of the Big Bang. For the first 380,000 years after the Big Bang, the universe was a super hot, dense soup of particles and radiation. Light couldn't travel freely. It was constantly bumping into electrons, but as the universe expanded, it cooled down. Eventually it got cool enough for protons and electrons to combine and form the first hydrogen atoms. Suddenly, the light was free. The photons that were zipping around at that moment were unleashed, and they have been traveling through the universe ever since. Today, 13.8 billion years later, we can still detect this light. It's all around us in every direction we look. It's the oldest picture of the universe we will ever have. This light is not perfectly uniform. There are tiny, tiny temperature fluctuations. Some spots are a fraction of a degree hotter, and some are a fraction of a degree colder. These spots correspond to areas in the early universe that were slightly denser or less dense than average. These were the seeds that would eventually grow into galaxies and galaxy clusters. Now, here's the clever part. Scientists could calculate, based on the physics of the early universe, how big these hot and cold spots should have been back then. They had a known physical size, so they had a cosmic ruler. They knew the size of an object, and they knew how far away it was, 13.8 billion light years. All they had to do was look at the sky and measure how big these spots appear to be. This is a direct test of the universe's geometry. Think of it like looking at a coin at the bottom of a swimming pool. If the water is perfectly flat, the coin looks its normal size. But if the water is acting like a magnifying lens, the coin will look bigger. If it's acting like a demagnifying lens, the coin will look smaller. In this case, the fabric of space-time is the lens. If the universe is closed and positively curved like a sphere, it would act like a magnifying lens. The spots in the CMB would appear larger than they should. If the universe is open and negatively curved like a saddle, it would act like a demagnifying lens. The spots would appear smaller, and if the universe is flat, there is no lensing effect. The spots would appear exactly the size that the calculations predicted. Satellites like MOP and Planck were built to measure these spots with incredible precision. They stared at the sky for years, mapping the ancient light. The results were clear. The spots were exactly the size they were predicted to be for a flat universe. The evidence was overwhelming. The universe has a flat geometry. The total amount of stuff Earth is matter, and dark energy adds up to the critical density. But this led to a new problem. A flat universe is actually a very strange and special case. It's a perfect balancing act. If the density of the early universe had been off from the critical density by even a tiny, tiny fraction, that difference would have been magnified over 13.8 billion years of expansion. If it was slightly too dense at the start, it would be wildly closed and curved by now. If it was slightly less dense, it would be wildly open and curved. For the universe to be so remarkably flat today, it must have been ridiculously, impossibly flat at the very beginning. This incredible fine-tuning is called the flatness problem. Why was the universe born with such perfect density? The leading solution to this problem is a theory called cosmic inflation. This idea suggests that in the first fraction of a second after the Big Bang, the universe went through a period of mind-bogglingly rapid expansion. Grew from smaller than an atom to bigger than a galaxy in an instant. Inflation solves the flatness problem beautifully. Imagine a tiny, wrinkled, highly curved balloon. Now, inflate it to the size of the Earth. If you are an ant standing on the surface of this giant Earth-sized balloon, your local patch will look perfectly flat. You wouldn't be able to detect the overall curvature. Inflation does this to the universe. It takes any initial curvature the universe might have had and stretches it out so much that our observable part of it looks perfectly flat. So, the current picture is this. The universe is geometrically flat. This is because the total cosmic inventory of matter and energy adds up to the critical density, and because of a period of inflation at the beginning that ironed out any wrinkles. But hold on, this story has another twist. So far we've only talked about geometry. We've talked about curvature, but there's another aspect to shape called topology. And geometry is about what happens locally. It's about the angles of triangles and parallel lines. Topology is about the overall global shape and how it's all connected. Let's go back to our 2D ant on the flat sheet of paper. The geometry is flat, but you can take that sheet of paper and roll it into a cylinder. The geometry is still flat. For the ant living on the cylinder, a triangle's angles still add up to 180 degrees. The parallel lines still stay parallel. Locally, nothing has changed, but the topology is different. Now, the ant can walk in one direction and end up back where it started. You can do something even stranger. You can take the cylinder and connect its ends. Now, you have a donut shape, or a torus. Again, for a tiny ant on the surface, the world still looks flat. The geometry is flat. But the topology is very different. Now, you can walk in two different directions and end up back where you started. So the question is, could our universe be like that? It has a flat geometry, but maybe it has a weird topology. Maybe it's finite. Maybe if you traveled in a straight line for long enough, you'd end up right back where you started, looking at the back of your own head. The universe could be shaped like a three-dimensional donut, often called a three-torus. Or it could have even stranger, more complicated connections. How could we ever test this? If the universe was connected in this way, like a hall of mirrors, we should be able to see it. As we look out into space, we are also looking back in time. If the universe were a three-torus that was smaller than the distance light has traveled since the Big Bang, we should see repeating patterns in the sky. We might see the same galaxy or the same cluster of galaxies in different directions. The cosmic microwave background provides the best way to search for this. If the universe had a repeating topology, there should be strange patterns in the CMB. For example, we might see matching circles of hot and cold spots on opposite sides of the sky. Scientists have searched for these patterns. They have combed through the CMB data, looking for any evidence that our universe is wrapped around itself. And so far, they have found nothing. There are no confirmed repeating patterns. This means one of two things. Either the universe has the simplest possible topology, it's just an infinite, flat expanse. Or it has a weird, repeating topology, but the wraparound distance is just much larger than the part of the universe we can see. Our observable universe, the sphere of space, from which light has had time to reach us. is about 93 billion light years in diameter. If the universe is a 3 torus, but the size of the torus is a trillion light years, we would never know. Our observable patch would be too small to see the repeating pattern. This brings us to the most important caveat in this entire discussion. Everything we have measured, everything we know, applies only to the observable universe. We have no idea what lies beyond our cosmic horizon. We don't know how big the entire universe is. It could be a little bigger than what we see. It could be 100 trillion times bigger. It could be truly mathematically infinite. We just don't know. So if the entire universe is vastly larger than our observable patch, then the concept of its overall shape becomes almost philosophical. If the universe is a giant closed sphere, but it's so big that our 93 billion light year patch looks perfectly flat, does it matter? For all practical purposes, our universe is flat. Inflation theory predicts that this is exactly the situation we should be in. The entire universe might have some overall curvature, but the part we can access is so enormous that it is indistinguishable from flat. So, what is the final answer? What is the shape of the universe? The best answer we have, based on all our evidence, is that the universe is flat. Its geometry is that of an infinite three-dimensional plane. But this comes with some footnotes. First, this flatness is a combination of all the stuff in the universe: normal matter, dark matter, and dark energy. The interplay between these three is what determines our cosmic fate. Right now, dark energy is winning, causing the expansion to accelerate. Second, this applies to the observable universe. The shape of the entire universe, the whole cosmic ocean, is unknown and may be unknowable. It could be a sphere, a saddle, or something far more complex, but it would have to be so mind-bogglingly vast that our local region appears flat. Third, there are still some lingering debates. While most data points to a flat universe, some analyses of the very precise Planck satellite data have hinted at a slight positive curvature. They suggest the universe might be closed, a giant sphere. This is not the consensus view. It contradicts other evidence, like the supernova data. Most cosmologists think it is likely a statistical fluke or a systematic error in the data. But it's a reminder that science is a process. We are constantly refining our measurements and questioning our conclusions. This cosmological crisis is an active area of research, so we are left with a picture that is both remarkably simple and deeply mysterious. The part of the universe we can see behaves according to the simple rules of Euclidean geometry. It appears to be flat, but it's a flatness created by a bizarre cocktail of ingredients, including matter we can't see and an energy we don't understand. And this flat patch of reality might just be one tiny corner of a much larger and possibly much stranger whole. The ultimate shape, the true nature of the entire cosmos, remains hidden from us, just over the horizon.